Hello and welcome to the second tutorial in the series on quadratic functions. Now, the first tutorial was very much an introduction. We just chose some simple examples of quadratic functions, and I sketched them and tried to bring out for you these really important concepts, particularly the symmetry that every quadratic function and or parabola, I'll sometimes refer to them as parabolas, that they have a symmetry, there is a mirror, sometimes called an axis of symmetry, and that it may be the case that the curve passes through the x-axis. The values of x where that happens we call roots, and the roots will always be equidistant from the axis of symmetry. So in this and the following tutorials I'm going to be more formal and introduce you to a set of tools which allow you to calculate for a given quadratic function things like its axis of symmetry and its roots and so on. But I'm trying to give you all of these tools in a kind of integrated, coherent way so you see how they're all connected. So here we are, quadratic functions continued. And in this tutorial then, we're going to look at the most general equation for a quadratic function, which is this: y equals ax squared plus bx plus c. So that is the most general form of a quadratic function y of x. Kind of interesting just looking at that actually, because in the last tutorial we quite easily were able to sketch quadratic functions that had the first and third terms. A number times x squared plus a constant wasn't too bad. This is the troublesome term. Why is that term troublesome? Well, it doesn't change anything about the concepts of symmetry or roots. But what it does is it moves the parabolas around in the horizontal sense, and it just becomes more of an effort to find the mirror or the axis of symmetry. So this term in a way is kind of the bugbear, and it causes all the problems. But do you also see that if we cross out the ax squared term, we have an old friend? That in disguise is our old friend, the equation of a straight line. So you see, a quadratic function is a straight line with an additional term, ax squared, and this term sort of magically takes a straight line and turns it into this beautiful shape that we call a parabola. Right, so I'm going to be quite general in this tutorial, and I just want to give you a sense of what parabolas will look like in this general form. So over here, let me say that I'm only interested in parabolas that have a greater than 0. And I'm going to draw 3 examples. And then on this side, in a moment, I'm going to look at the same thing, but for a less than 0. Okay? Here are some coordinate axes, and I would like to have 3. Something like that, I think. Right, now as I say, this term bx, it pushes the parabola to the left or the right. If we just quickly go back, look at the first tutorial, the notes here. We were actually looking at parabolas like x squared plus 1 or x squared minus 1. And all of the parabolas that we drew in that first tutorial were symmetric about the y-axis. Adding this term bx is not going to change the shape or the properties that we talked about, the symmetries and so on, but it's going to move the parabola around. Precisely where it moves it to depends on the values of a, b and c. But move it around it will. And so for some values of a, b and c where a is positive, we may have a parabola which looks like this. Do you see that there is a mirror? The mirror goes through the minimum value of this parabola. In subsequent tutorials, we're going to find out how to find the value of this axis of symmetry, what value of x it cuts through here. Do you also see that this parabola never cuts through the x-axis? So it has no roots. On the other hand, depending on the values of a, b and c, although I'm taking a positive here, we might have a parabola that looks like this. Well, it has a nice axis of symmetry. Okay. This time it does cut through the x-axis, and here are the two roots. Now, I didn't draw this parabola brilliantly, but these roots will always be equidistant from the mirror, from the axis of symmetry. And as I said before, we will learn some tools to be able to calculate the value of these roots. So here we have two, I'm going to call them distinct roots. Now, the intermediate case, you can probably guess, is when it's not above the x-axis or below the x-axis, that it actually just touches, just grazes against the x-axis. And this would look something like this. We have an axis of symmetry, but it only touches the x-axis at one place. That's the intermediate case. This gets a little bit pernickety in the old days. The way I was taught, we talked about there being one root. I know in the Scottish curriculum, though, students are not rewarded for saying one root. They have to say two equal roots. Now, it probably is best if I don't give my opinion on this, because it's probably not terribly helpful. But it's a bit like having a single child and calling that child two equal twins or something like that. However, the intuitive point is that the curve touches the x-axis at one point. And in the Scottish curriculum, students have to say that there are two equal roots. As I say, in other curricula, it may be that students are encouraged to say there is one root. But those are the three possibilities if a is positive. Very, very important point. The sign of the constant that multiplies x squared determines absolutely the gross shape of the curve. If a is positive, you will always have a parabola that is in the shape of a valley, or a U, if you like. The values of b and c will push this U-shaped curve around, up and down and left and right, but they can't change the fact that it's a valley-shaped curve. Now let's look at a negative and just do the analogous thing. I want to draw three different parabolas with a negative and see what the possible outcomes are. Okay. So a negative, we know we're going to have a curve now which is a hill-shaped curve. It might be that the curve looks like this. Okay, so it has a nice axis of symmetry. All of these parabolas will always have a nice mirror. Now in this case, this curve has passed through the x-axis in two places. It has two roots. I just have to keep making sure, as good kind of practice, just to label the axes. You know, it's a very good discipline to get into. Otherwise, one doesn't know what one's looking at. So here's my first example of a parabola with a negative. The values of b and c, I don't know, but in this particular case, it looks like this, and it has two roots. And again, there's a mirror of symmetry, and these two roots are equidistant from that mirror. So again, here, for this particular one, we would say there are two distinct roots. It might be that it looks like this. It has a nice symmetry, but it doesn't pass through the x-axis. Here we would say there are no roots. And then the intermediate case, which I wish I'd drawn this axis a bit higher up, but never mind. The intermediate case will look like this. There it is, really not a very good parabola. That's a bit better. So it has a mirror of symmetry, and it just grazes the x-axis at one point. And again, depending on the era in which you're learning this and the geographical location of your exam board, you might either call this one root, or certainly in Scotland, to get a mark in an exam, you have to say two equal roots. Okay. But the key point is it touches the x-axis at one value of x. Now, these are all the possible sort of forms of parabolas that you can get from this formula. They might be on the left-hand side of the y-axis, but the key point really for us in terms of roots is that if a is positive, it's a U-shaped curve that's either above the x-axis, below the x-axis having two roots, or just touching the x-axis having two equal roots or one root. If a is negative, it's a hill-shaped curve, either passes through the x-axis with two roots, just touches having one root or two equal roots, or is below the x-axis and has no roots. So, as I say, these curves can be left or right. I've just drawn them all on the right here because I have to sort of make a choice in sketching them. But there will not be any other shapes that you have to worry about. So one question is, how do you know, let's say, how do we know what's often called the nature of the roots? Namely, are there any roots? And there's a lovely way to find that out, which is really simple, and it uses something called the discriminant, which I'm going to try and write in kind of a non-cursive here so that you can see exactly how it's spelled. Discriminant. The discriminant. Hope I spelled that right. Discriminant. And the discriminant is literally, it discriminates these different cases. It is the quantity b squared take away 4ac. So if someone gives you a parabola and says, tell me about the roots, you don't have to sketch it, you just take the values a, b and c in that parabola or that quadratic function that you're given, and you simply form this combination, b squared take away 4ac. If this is positive, then you will have two distinct roots. If it is 0, you will have one root, or let me say one root. I'm putting that in quotation marks because I know in Scotland that's not something that you would get marks for. You have to say two equal roots. And finally, if it's negative, there are no roots. Now, in the final tutorial in this series, I'm actually going to go beyond the kind of typical curricula at this age range and derive this for you so you can see exactly why it's the case. And that's optional. You may not want to go into that much detail, but what you do need to know is that if you're asked about the nature of the roots, do they exist, how many, and so on, you need to look at the combination b squared minus 4ac, and if it's positive, you have two distinct roots. If it's 0, you have these cases of there being one root or two equal roots. If it's negative, you have these cases here of no roots. So this case and this case would have positive discriminants. These two cases have a 0 discriminant, and these two cases have a negative discriminant. Now I'm going to be giving examples of particular quadratic functions in forthcoming tutorials, so don't worry if this seems a little bit abstract at the moment, but I am trying to stress the generality of this, how powerful it is that no matter what the values of a, b and c, this is the combination that you need to calculate the discriminant in order to talk about the roots. Also, that these are all the possible shapes that you can expect. Now, I have to say one last thing before moving on, and that is that in Scotland, and I suspect in many other school boards, you actually have to add another word to describing the nature of the roots. And I've sort of left that word out up till now because it's probably very confusing. But you have to add the word real. Okay. The word real. And you have to add that. You have to say two real distinct roots, or two real equal roots, or no real roots. And there's a perfectly good reason why in mathematics that you need to say that, but it's a fair bit beyond the level of this curriculum. So in that final tutorial, when I derive the discriminant, I will say more about that, but to be honest, it would be confusing for me to go into why you have to say the word real, but just take it from me that that's what's expected of you to say. And if you're curious about that, I'm very happy to go into that in the final tutorial in this series. I hope if you've been following along with these that you really believe that my aim is always to be as clear as possible and to avoid sort of boring lists of facts and sort of rules in maths. Maths is about having fun and having confidence, and everything is connected, and it's about understanding those connections. So clarity and transparency are key aspects of teaching maths, and I really, really hope that I'm able to provide that. And if I'm not, I would really enjoy hearing from you so that I can make sure that I improve in that aspect. Right, so we're done for this tutorial, and in the next tutorial I will be talking more about roots and how to calculate them. So thank you so much for your attention with this difficult topic, and I'll see you next time.